All right, so continuing our review for chapter 6, decimal basics is stuff from 6.1. Fractions versus decimals is still section 6.1. And the models with base 10 blocks, that was section 6.2. We just reviewed section 6.3, which is about mostly percentages, but ratios and proportions too. So let's take a look at decimal basics. So when we use the word decimal, remember, it just means based on 10. And so all of the numbers we write, like 15, 7, 3,721, the year, 2021, these are all decimals. But often when people hear the word decimal, they think about things like 0.25, which is also a decimal. These guys right here differ from those because they are actually decimal fractions. And with decimal fractions, we basically throw out denominators like 3 and 7 and 9 and 11. We throw out a ton of different denominators and say, hey, only denominators based on 10 are allowed now, which in some sense makes life easier, but in another sense it makes life harder because then numbers like 1/3, 1/9, 1/7, 1/11, they're more trouble to deal with. So pros and cons of decimals. Numbers like this right here, we often say slang and call it 0.25. That's not the meaning of this number, right? The correct way to read that would be to say, hey, that's 25 hundredths because the 5 is in the hundredths position. Right? Its place value is 100. We can also write this as an expanded form. I have 2 tenths and I have 5 100ths. And we started off playing with base 10 blocks to show what that looks like. And so if we whipped out our base 10 blocks, often we used, I'm gonna see, 1, 2, 3, 4, 5, 6, 10's down there. So if I say this right here is 1/10, right, then 2 of those would be 2 tenths. And then I have my combination of the 500. So if that's a 10th, then this would be 100th, right? So 1/10, 1/10, and then we can draw out 500ths. And they should be roughly proportional. So it should look like 10 of these make that, and 10 of those make a whole flat from our pieces. So 1, 2, 3, 4, 5. So these are our 500ths. Our expanded form can also be written with exponents. So this would be 2 times 10 to the negative 1 plus 5 times 10 to the negative 2. And remember, negative exponent just means flip the base. Another idea I thought was an important one that some kids struggle with at first is they're used to having their 1s and their 10s and their 100s and so on. And then we throw this decimal point in and we throw these new places at them. And they want the decimal point to be the kind of the center of all this, but it's really not, because here I have the tenths and the hundredths. And a lot of kids are left kind of like wondering, or there's this missing thought that they just never could quite grasp, like there's something missing here. And it's not the decimal point that's kind of the center of this system, it's the ones place that's kind of the center. And then distributed on each side, we have our tens and our tenths, our hundreds and our hundredths, right? And ones are the middle of it all. That's kind of an important idea too from the decimal basics. Again, the problem with these base 10 fractions is things like 1/3 and 1/7 are much harder to deal with. Way go. So fractions versus decimals. I can easily just read a decimal properly to get a fraction by just saying that's the tenths, hundredths, so this is 5/100ths. And I can reduce if necessary. So this one reduces, sometimes they don't. So dividing top and bottom by 5. I can say this is also 1/20th. Going the other way is a bit more work. So if I have a number like, let's say 1/8, how do I change that to a decimal? And the trick is to realize that this is a division, that we're taking 8 into 1. Right? 8 goes into 1 how many times? And that's where we have to apply our division algorithm. And the division algorithm we developed says, well, if you need more decimal places, you just put the decimal where it goes in the quotient. Well, 1.0 is still 1, and you can put as many zeros as you want out there. It doesn't really matter, it's still 1. That tells you where the decimal goes in the quotient, the answer, and then you just divide, making believe you have whole numbers. 8 goes into 1, 0 times. 8 goes into 10, 1 times. 1 times 8 is 8. And then we just keep going until we decide we're done, and that decision comes in one of two ways. So remainder 2, bring down the 0. 8 goes into 20 twice. 2 times 8 is 16, subtract, bring down the next 0. 8 goes into 40, it goes in 5 times. 5 times 8 is 40, subtract and get a 0. Right, so that's one stopping point. Zero remainder. Now 8 worked out pretty good. It had a termination point, but it doesn't always work so well. So let's suppose I was going to do like 3/11ths. Right, so that's 3 divided by 11, or how many times does 11 go into 3? So we can also write it as 11 goes into 3. And then we can just say, hey, well, 11 doesn't go into 3, but we know that we can put as many zeros here as we want and see what happens. So 11 goes into 3 0 times. That point is important to line up where the decimal point goes. 11 goes into 30 twice. 2 times 11 is 22. Subtract. 30 minus 22 is 8. Right? Bring down that 0. 11 goes into 87 times. 7 times 11 is 77. Subtract, and I get a 3. And the question is, well, when do we stop? Well, usually we stop when we get a 0, but we don't always get a 0, so let's just keep going for fun. Bring down that next 0. 11 goes into 30. Hey, that sounds familiar. 2 times 11 is 22. That looks familiar too. We've done this before, haven't we? Deja vu. Subtract, bring down a 0. 80, right? And we're starting to repeat ourselves now. Question is, what signifies the repeat? Is it the fact that we see a 2 here and a 7 there and another 2 and a 7? Or is it that I see some repeated remainders? Here's a remainder of 8, there's a remainder of 8. Here's a remainder of 3. That's essentially a remainder of 3. It's a part of the whole. And it turns out the repeating remainder is the more important part. So we're going to keep getting a remainder of 3, then 8, 3, then 8. Now that leads to a quotient that's a 2 and a 7, a 2 and a 7. So then we can say 3/11 is equal to, and here I'm going to use slang because it really doesn't make sense to talk about it the other way, 3.27 with just the 27 repeating. And it's kind of weird to say it's 27 hundredths repeating because the next place aren't tenths and hundredths, right? This is tenths, hundredths, thousandths, 10,000ths. So putting the repeating symbol and reading properly is kind of awkward. So that's one place I do use slang on purpose. All right, so overview of decimal basics there. Reminder, for those of you who aren't the best drawers like me, the Math Learning Center, and I have links to it in other places, have that number pieces app. Number pieces that we've used plenty of times before. Oops, button again, too many buttons. And I prefer the other version, which you can switch to at the bottom, where you get colorized pieces. And the cool thing about the colorized pieces is if you use the split apart or break up pieces button, it changes the color to say, hey, this is no longer a whole 10 or a whole tenth or whatever we're calling it. It's now those little pieces there. And so often when we did this, we had for our key on these that the flat one whole, and this green long here was 1/10. And that little yellow piece then was 100th. But we could make other choices on that, but this is the one we almost use almost all the time when we're playing around with these pieces right here. All right, so out of decimal basics, moving into modeling operations. Operations does not have two P's, does it? There we go, that's better. So remember what a model means. A model has to explain why. Versus an algorithm, which is just, how do you do it, right? So back here, this one right here, I was using a division algorithm to do this. I didn't really explain why. I didn't draw any pictures. I'm just saying, hey, follow these steps, you'll get the answer. So that's an algorithm. It's a series of steps. A model explains why do you get the answer you get, not just how do you get the answer you got. So again, the key is why. And with models, I always ask you to illustrate and explain because I have actually a physical model, okay? Often the base 10 blocks. So let's look at subtraction. And I'm going to take subtraction to be a comparison. The takeaway works okay too. And let's see, what problem should we do? How about 1 25/100ths minus 45/100ths. And so to do this, I just want to know how much bigger 1 25/100ths is than 45/100ths. And I want to use base 10 blocks to do it. Right, so what does subtraction mean? Subtraction means compare. Here's the problem. What does that mean for these numbers? So how much bigger is 1 25/100ths than 45/100ths? question marks. So then I whip out my base 10 blocks. And now I'm going to move over the app to show these. And we're going to use this model here for flat as a whole, long is a tenth, and the unit is 100th. And I just want to show here mostly I'm going to copy and paste this stuff to my other screen. So to do that, I need to show my 1 and 25 hundredths. Versus my 45 hundredths. And the hundreds work out pretty good, right? Because I have a pretty much direct match with those. Actually, I kind of like the way they work. Ooh, I always do that. One button. I think I like this way better for that comparison. So I can match those up pretty good. There's a 5 to 5, 1 to 1 comparison there. But the tenths don't work out so good. So really, I can't do a direct comparison until I trade. So let's just copy this to draw on it a little bit. Let's put these next to each other that way. I got a problem here in the comparison. We don't have enough tenths. So we got to trade. Otherwise, I can't continue the comparison. So I'm just going to make a copy of these guys. Oops. Duplicate the button there. Nice. And then I can take this one and just break it up. So I have the same numbers. I still have 1 and 25 hundredths. I'm now looking at it as 12 tenths and 45 hundredths, because then I can compare these guys. So I'm kind of running out of colors, so we'll just cross them out. So this number here is still 1 and 25 hundredths, but I'm viewing it as 12 tenths and 5 hundredths. Right, we could use decimal notation on that. I just rewrote it as 12 tenths. 1.2 is properly read as 12 tenths or 1 and 2 tenths and 5 hundredths versus my 4 tenths and 5 hundredths. And so this guy matches that guy, and this guy compares to that one, and so on. Compare, 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 compare. Sometimes we draw lines connecting them, whatever you want to do there for your comparison. And then I want to compare these guys. So one of those to one of those, and so on. Trying I'm gonna make a diagonal, but I'm having trouble with my digital pen today. Okay, and then I can see here what that leaves. Eight tenths. So 1 and 25 hundredths is 8 tenths more than 45 hundredths. Okay, so this shows why the answer ought to be 45 hundredths. You guys know a lot more than the kids do. You're used to the algorithm where instead of writing it out lengthwise like this, we stack. And at first, this subtraction goes pretty good. 5 hundredths minus 5 hundredths is 0 hundredths, but then we run into this problem here where we can't take 2 from 4 and we have to borrow, oops, wrong place. We have to borrow from here to make that 12 tenths, right? 12 tenths. So this right here justifies our borrow. Over here. So that's the point, really, of using these toys to show this. So we justify why the algorithm works because of the trade over there. So 12 tenths minus 4 tenths leaves me with 8 tenths, and 0 minus 0, there's no ones. So the trade, 1 whole, 10 tenths, is why we can borrow in the algorithm. Right? Algorithm, nothing about why, it's just here's what you do, follow those steps, you get the answer. Model explains why. So you need to differentiate between a model, why things work, algorithm, how things work. Questions on this one? In addition, we would join, and that represents the carry. So I'm going to skip addition for now. It's pretty similar, look at multiplication. Typically with base 10 blocks, we look at multiplication as an area. And with an array, we have a base times a height. And let's see, what should we do? How about 2 and 3 tenths times 1 and 4 tenths? So I want to illustrate this. So I want to know what is the area for a base of 2 and 3 tenths and a height of 1 and 4 tenths. And so we're going to then look at the area and find the answer. So first we have to draw this out. And if you have trouble with graph paper or drawing it by hand, you either need graph paper or a ruler to make a good sketch of this. Otherwise, you're going to have to resort to the blocks here. So I'm going to do it on paper first and then go over the blocks. So I have to show my base and my height on this page here. So let me mark some stuff off. Instead of go that high, 1, 2, 3, 4. 2, 3, 4, 5, 6, 7, 8, 9, 10. So that's going to be my height there. And then coming across, I've got 2 and 3 tenths. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And let's just make that mark. Can I just duplicate you to get another one? Come here. So. So here's what that one ends, and then 1, 2, 3. So that's 1 right there, 2 right there, so that's 2 3/10 right there. This is 1 right here, 1, 2, 3, 4/10, so this would be 1 4/10 there. So now this shows me what my area looks like. So I measure it out. So that, my answer lives in there, I just have to now break it out of that. So once I draw the shape correctly, then I usually mark it off in terms of where the decimal point would go. The decimal point goes between the 2 and the 3/10 and the 1 and the 4/10. So this kind of splits it into 4 regions, and those 4 regions are related to our expanded algorithm, which we'll show in a minute. And then from there, really all we need to do is mark off the holes in the extra tenths. So I don't need tenths everywhere, I just need them on the edges in the fractional parts of the number. And then I'll just make a note of what I see roughly and see if I can clean it up at all. So when I look at this right here, I see 2 holes, right, in this region right here. I'll highlight that. So we can clearly see 2 holes over there. And then let's say over here, I see 3/10, right, in this region right here. Up here, I see 1, 2, 3, 4, 5, 6, 7, 8. I see 8/10 up here. And highlight those, choose a different color for the tenths, about greenish. Right, so here's my region of 8/10, my region of 3/10 down here. And then I have a whole bunch of hundredths over here. So maybe I'll highlight those suckers in yellow. How many do I have there? Well, that's a 3 by 4 grid. 3 times 4 is 12. So I see 12 hundredths there. And then we want to notice if we can do any trades in this picture. So in combination with these 2 right here, I have 8, 9, 10, 11. So I can do a trade on that. So I could make a note, trade 11/10. There's a bunch of ways to word this for 1 whole and 1/10. So that's 1 trade that's going to happen. And then I can do a trade here too, because I have 12 hundredths, right? Read that properly. Don't read this 0.12, it's 12 hundredths. So I can also do a trade there. So I'm going to trade 12 hundredths for 1/10 and 2 hundredths. And those trades should mark any place I carried a digit to the next place value over, and we want to show that in either the expanded algorithm or the standard algorithm. But let's finish cleaning this up. So altogether after the trades, so after trading, I had 2 holes, I now have another one, so I have 3 holes. Trouble with my pen here. And as far as the tenths go, I had 1 leftover tenths from those, and I traded for another 10th there, so I see 2 tenths here. And after the trade of the hundredths, there were 2 hundredths left over. All right, so it looks like our answer is 3 and 22 hundredths. 3 holes, 2 tenths, 2 hundredths. So now looking at algorithms to go with this, squeeze those in underneath, expanded, and then standard. So I would write, say, 1.4 times 2.3 And then 3 times 4, right? We write the 2, carry the 1. So there's 1 carry from up here. And then I do 3 times 1 is 3, plus 1 is 4. And then fill in a 0. 2 times 4 is 8, right? There's those 8 there. And then 2 times 1 is 2. And then come down, 2 and 0 is 2, 8 and 4 is 12. There's another carry right there, right, which relates to that. And then there's the 3, 2 decimal places in the answer from those guys. Oh, that's not the expanded, that's the standard. Lost track there. Sorry about that. Do the expanded next, apparently. Standard algorithm. All right, let's do expanded next. And with the expanded algorithm, we usually think about place value. So with the expanded algorithm, 4/10 times 3/10 is 12/100. And we just write the whole 12 underneath. And then 3/10 times 1 whole is 3/10. And then 2 wholes times 4/10, 2 groups of 4/10 should give us 8/10. And then 2 groups of 1 is just 2. And so in the expanded algorithm, I should see each of the regions above, right? So here is my yellow hundredths from here, and then my green tenths here and here, and then my wholes here. And any place I skipped over into more than one places, we have a carry going on. So I'll circle those carries. Oh, I guess I'm not done. Then we have to combine all of this to 8, 9, 10, 11, 12, carry, 1 plus 2 is 3, decimal point lines up. And so the carries happened here and here, because that used up more than one place, that's a carry. So the trades correspond to carrying. All right, questions on multiplication? So most of the work on the page is my modeling. I'm trying to justify why should the answer be 3 and 22/100ths? Well, because multiplication means area, and here's what this area looks like. We can count the answer from the area using the base 10 blocks. Under the red line down here, I have my algorithms, and they don't explain why the answer is 3.22. They just show how to get an answer of 3.22. This is just how, not why. And I need you to be comfortable with the how and the why, which is very challenging. All right, next, division. Now, division's always the hardest of the 4 operations, 4 basic operations. And because of that, we're kind of limited as to the models that we can make to do this, because otherwise they're just too hard to construct. And so typically we play with tenths and hundredths, or just hundredths and hundreds, but usually it's tenths and hundreds. So then here, I am just going to mark off a region that's 10 by 10. 5, 6, 10. And again, if you don't have graph paper, you have trouble drawing this, those blocks online are a cool thing to do. Oops. straight line tool. There we go. And so we're going to use the standard idea that this 10 by 10 grid is one hole. And then let's suppose, what should we do? How about, let's do 56 hundredths divided by, how about 14 hundredths? And so then we have to come up with what's a definition for division. So we got a few different options here. We could use the idea of groups of, we could use the idea of repeated subtraction. I think those are the easiest two to use here. So I could say what this means is division is groups of. And then state what that means for these numbers. So that would mean how many groups of 14 hundredths are in 56 hundredths. Oops, percent. What was that? Question mark. And when we state this sentence like this, we're basically kind of setting up a long division. 14 hundredths goes into 56 hundredths how many times? Well, I need to see what 56 hundredths looks like over here, so I would have to shade that in. So let's build our 56 hundredths, let's say in yellow. So we have 5/10. So 1, 2, 3, 4, 5. Outline that 2 in a second to be clear, and then 6. So 1, 2, 3, 4, 5, 6. So this right here is my 56 hundredths. Check. 10, 20, 30, 40, 50, and 6, yeah. 56 hundredths. And then I want to look for groups of 1.4, so I got to find a way to show those. Let's see, I guess I could just draw those in, let's try in blue. So that would be, right, 10 of these, no, that's kind of messy. 10 and then 4, 1, 2, 3, 4. So this right here could be my first group. Trouble being neat today. All right, so there's one group there, and then what's that leave me? 6 here, and then I would need another group, 7, 8, that much right there. There's another group, 6 and 6 is 12, 13, 14 hundredths. And then 1, 2, and 10, and another 2 over here. I'm sure there's lots of ways to draw this. There's another group, and then I have, what, 8 there and 6. There's another group. So I have 1, 2, 3, exactly 4 with none left over. So there are 4 groups in there. Four groups of 14 hundredths in 56 hundredths. And a thing to note about this right here, I was just focused on 100ths. And when I made the 5600, right, I counted 10, 20, 30, 40, 50, 1, 2, 3, 4, 5, 6. And so I'm thinking about these as individual objects. And so the point is that 14 hundredths goes into 56 hundredths. Means the same thing as 14 goes into 56 how many times? And we get 4. They mean the same. And that kind of gets at our algorithm. And our algorithm basically says that the long division works best if our divisor is a whole number. And then we adjust the numerator to compensate. Let's just review that algorithm. So this is the model. This one showed why should the answer be 4? Why isn't it something else? Well, because division means groups of, and there happen to be 4 groups of 14 hundredths and 56 hundredths. That's it. That's why. Because that's what division means. Now the how is the algorithm. So remember steps of the division algorithm. Meaning long division, not whipping out calculator, because it has its own algorithm that's not quite the same, but works the same in the end. So number one is we want the divisor to be a whole number. Two, we adjust dividend by the same number of places. Three, we mark the decimal in the quotient. 4, divide like with whole numbers. And there's kind of an extra step there, adding zeros if necessary. Sometimes we need to, sometimes we don't. Right, so for the problem we were just doing, we had 14 hundredths goes into 56 hundredths how many times? And to do that model-wise, we really thought about hundredths as whole things, so we moved the decimal over there, and we really had to do the same thing with that right there. So that, I had to move those. So that means this problem is the same, and I often have young kids that are new at this rewrite it so it's not so messy, as 14 goes into 56. Now, the decimal point's now here, so I mark it in the quotient above, and after that, if I need zeros, I add them. If not, that's where it ends, right there. Okay. Now, I don't know my 14 tables too well, so I kind of got to guess. 14 plus 14 is 28, plus another 14 is, what, 30, no, 42, plus another 14 is 56. Ah, there's 4 of them. 4 times 14 is 56. Cool, 0 remainder. I don't need any more zeros, I'm done. When we played around with, what was it, 3 goes into 11. Now this already was a whole number. All I had to do, I didn't have to do anything for the first 2 steps. I just needed to mark the decimal in my answer and then add zeros as necessary. So that's the division algorithm. Nothing to do with pictures, although the pictures kind of explain why we do it that way. It's just, how do you get the job done? What are the steps to do this? All right, so that is a review of almost everything. We're about out of time for fun with math. Man, time flies. Do you guys have any questions about stuff you were struggling with that I didn't go over?